Pablo Nicolaitis. I am the build team lead. I'm going to walk through our frame design a little bit here. So we stuck with square aluminum tubing, just kind of kept the frame as simple as possible. We've had a couple years of experience for the NASA robotic mining competition building very similar frames. Basically just a square box to hold the electronics on the inside, and then we have our suspension system. It's a kind of simplified rocker bogie system. We wanted to avoid the complicated pivots that required. So we have independent suspension in the back, strictly vertical movement, so there's no camber issues with the wheels. In the front we have a rocker system on a suspended arm. The intention for that is just added mobility over rough terrain. Where we got a little bit more complicated in the design is the integrated hubs for the wheels. Historically we've had challenges in getting solid power transfer. So this year a big critical component of the design was direct power from the gearbox to the wheel. So we have an integrated bearing hub that houses the sim motor and Versa gearbox, and then the wheel will be mounted with carbon fiber plates directly to it. So a number of our design choices were determined by manufacturability concerns. Basically, we are kind of limited in terms of what we can manufacture, especially when it comes to custom components. So to kind of allow for a little bit more flexibility in the design process of the wheels, we've opted to go for a 55 aramid, 45 carbon fiber mix composite wheel hub on each side that will then take the power through the motor shaft. So we will be mounting our sample drilling system in the back of the robot to drop down, take our core samples, and then our arm and manipulator will be up in the front of the robot.
My name is Abram Malknagel. I'm the president of the University of Iowa Robotics Club. I will be talking about our electrical systems today. We have two Arduinos that control the robot. We have one Arduino that controls the driving of the robot, the drivetrain, and another Arduino that controls the arm. For the drivetrain Arduino, we are controlling 3 Nostro Systems motor controllers that in kind control 6 sim motors. We chose these Nostro System motor controllers because they can supply 70 amps continuously, up to 200 amps when they're pulsed. This beats out most of the other motor controllers that we were able to find, and since we're using sim motors that can stall at 133 amps, we needed something more powerful, which is why we chose the Nostro Systems motor controllers. For the ARM Arduino, we have a series of linear actuators and servos that control the arm and the hand motion. So we have a couple Polulu motor controllers that control the linear actuators and some servo motor controllers attached into that Arduino. Additionally, on the robot, we have laser rangefinders, a GPS device, and several cameras for both vision processing and getting the scientific photos that we need.
Hello, my name is Connor Grierson. I'm in charge of the science division. We are currently developing a system that's going to be able to take a panoramic picture of the environment to try to look around for water. We're also developing a digger system, which is going to dig 5 centimeters below the ground and then extract 5 grams worth of material, then to be analyzed by our Raman spectrometer that we're developing. We will then be inputting a probe that measures humidity and temperature inside of the newly dug orifice in the ground. This will lead us to an enormous amount of data that we can analyze from the subject.
I'm Emma Hawk, and for our control systems for this robot, we have a control systems laptop which communicates over Wi-Fi to a NUC, which is on the robot. And the NUC then talks with the Arduino. There is a program on it that starts automatically when it gets turned on, and it waits for communication from the control laptop. And it communicates with the Arduino. The Arduino is then hooked up to all of the motor controllers that we have. And so we're able to send signals from the control system to the NUC, which then talks to the Arduino. For the autonomous part, we're hoping to have some kind of GPS, which is able to use the coordinates that we're given, the goalposts, and then have cameras on the robot so that we can have visual tracking to find the tennis balls and sort of adjust where we are and make sure we can make it towards the goalposts properly.